long ago, people looked up in the sky and saw the sun rising and setting, and they said the sun must go around the Earth. And today, some people still think that, but we're here to talk about how that model has changed over the years. My two guests have been on here before in our famous Before Earth series, but it's been a while, so I'll let them introduce themselves.
Sure, I'll go first. Hi, I'm Dr. Tapioca Weasel, also known as Michael Vandegraff. My friends call me Vandy. And I am an atomic physicist who is currently doing his postdoc at Stanford University.
Yay. And I am Landon Curtin-Knoll, astronomer, planetary scientist, and I also get to study this planet as well as other planets, so I tend to focus on inner solar systems. So this discussion is going to be about the history of models of our solar system, how various models came about. So many of these models we're talking about we know are incorrect, but we're talking about more of the history of some of the major models. Now, there are many models. It turns out there are hundreds of models from various aspects of civilizations. We're not going to go into every particular model and its nuances. We're going to pick out a couple of eras and a couple of models from there. And it's going to be more than just simply saying, well, they were ancient people and then Greeks and then Copernicus and Galileo and Newton, and then we're done, right? There are actually some interesting nuances that came about, how models evolved. And in particular, you'll see an era where people sort of said, this is what we think the model universe is. And there's a whole bunch of people who say, well, the universe should be like this, so therefore this is the model that fits it, as if the universe behaved according to their ideas, or they were more saying a good universe would be designed like this, to models that tried to interpret what was going on in the sky, to models that became testable, testing and verification, and moving on. So we're not really interested in debating somebody who thinks the Earth is flat or the Earth is the center of the universe, that sort of thing. We're going to be talking about the history. And again, I apologize if we don't describe one of your favorite ancient models. We only have a certain amount of time, but that's the idea. Any other comments on that before we get started?
So do we know when or where the first model of the solar system came from?
We don't know the first models of the solar system. We have early archaeological records where people were talking about it. Probably today, the earliest known sort of model or diagram was called the Nebra Sky Disk, and it was something that was discovered on a site in present-day Germany, near Nebra, and our archaeologists date it back to about 1600 BCE, and it was basically a bronze diagram showing discs that they think were people trying to say this is what the sky was like. So that was more of that's a sort of they originally thought it was a Bronze Age artifact, but it's sort of been reformed later to Iron Age. So those are some of the earliest we know of. There are other writings that you will see in ancient Egypt, as one of the places, and Mesopotamia and so forth. There are that come into play, but I think it's hard to say this is the first model. I suspect that people were.
Is this the disc?
Yes, that disc. That disc is there. So it's kind of interpreted, and there's debate whether or not this is just a symbolic sky map or it was a model. You can kind of depend upon on there. But I think early on we find a couple of things. We find in the Near East they had this concept of what's called the firmament, and many Near East things, including biblical cosmology and ancient Hebrew cosmology, sort of had this vast dome created by God during the creation of the world to divide it from the primal sea and land. And so the sky was the dome thing, sort of the firmament, the thing up there. And so you could argue whether or not those models, again, not just the biblical model or the Hebrew model, but other ones in that area, you could argue whether or not that firmament was a single thing or complex things. But generally, the notion of it's up there, not here.
How did people learn about those weird moving stars that they called planets?
Well, it's if you pay attention to the nighttime sky, you will know people saw stuff moving around. And we know early on people knew that the sky was not just a bunch of random dots, right? That things moved around. And in particular, there were bright things that moved around with respect to other things, right? It wasn't just a single blob. It was there were wandering things. And then there were visiting things coming through the sky. So we kind of knew that there was stuff up there or things up there change. If you're doing the firmament, it's like the sky dome thing. The Babylonians, on the other hand, kind of this notion of they spent a lot more time. One of the things that they had going for them was a writing system that some Babylonians could write down stuff that other Babylonians could read and interpret later on. And in particular, they were some of the earliest known civilizations that began to see patterns with regards to eclipses, lunar eclipses and solar eclipses. And they saw the pattern of the moon going around versus the stars going around, had this sort of 12-to-1 ratio. And that sort of led them to believe, talking about sort of having a moon thing being there, although it wasn't quite a month, but it was close enough. And they started thinking about the zones of the sky, because the sky was rotating slower than the moon. And it was also Babylonians were able to, because of the writing, begin to predict, notice that the eclipses had some periodicity to them. They couldn't kind of completely, but they weren't just random things happening, and that they could begin to predict, particularly lunar eclipses was easier for them to do, and then some and
part
partial
of that's
solar
because
eclipses.
they happen a lot more often, right?
Yeah. Also, it's a lot more. It's a lot more visible. A lunar eclipse,
yeah,
with the moon going from the sun, is much more visible.
Solar eclipse is only really visible if it. I mean, it's obvious if it's complete, but if it's partial, it has to cover a lot of it for you to really notice.
Yeah, and the Babylonians, had notions of these cycles, the cycles between the sky moving and the moon moving, and seeing the lunar eclipses there, but also the solar eclipses. When they would see the moon, they saw the phases of the moon, from the moon being full to the moon being, they call new. And they saw that on occasion they would have a lunar eclipse. And they weren't necessarily able to go to the point of saying it's going to be total here, but they could begin to see partials going forward. It wasn't perfect, but it was a pretty good thing. During the same time, Chinese started having their sort of one of the first theories that we read about in China is this celestial lid theory. And there was a mathematical text by Zhai Jing around 100 BCE, where the Earth was within the heaven, and that within the heaven, and heaven acts as a dome or lid.
Hey, real fast. Both, I gotta say real fast, as earlier, both of you should be able to control the presentations on the screen right here. If you want to, just hit the arrow buttons back and forth.
And I'm just talking about if we're into part one, if you want to do that. Again, those are just notes on there for people to see. But again, we're talking about Chinese theories. There was again this celestial lid or celestial sphere. There are kind of two things there. There was sort of this. There are other people that Chinese theorists that talk about this ubiquitous darkness. That without the sun, you'd have this sort of darkness, implying that the sun and the moon were just highly dense vapor that floats freely in space with no periodic motion. Was kind of interesting thing that contrasts to some of the other stuff. And if you look at Chinese works in Nanjing Observatory, one of the really treasures of the world, it has continuous records going back for several thousand years where the practice was 5 people would face the 4 compass points and someone up, and they would just describe everything that happened in their view of the sky. And a lot of it was bird flew here, cloud here, rain here, blah, blah, blah. But they'd also say, comet there, bright star there that went away, eclipse stuff. And while it's difficult to interpret some of those writings because the Chinese characters several thousand years ago are much different than they are today. So you have to have people who know how to read ancient Chinese text. But and they described it in their day, but they would describe wandering planets getting near to the moon going in front of Saturn or Jupiter, to eclipses and so forth. They describe these things, and this gives us a very, very long baseline. So the records that were there, it was fortunate that Mao Zedong failed to destroy the records of this this treasure, because he did a lot to destroy a lot of ancient Chinese culture. But hey, that's a different story. So Chinese had several different models: celestial lid, celestial sphere, and ubiquitous darkness models. The Babylonians had more cyclic stuff, particularly in eclipses, and some of the stuff about we get from the 12 months, the 360 degree circle, right? That notion of 360 comes from, they saw it as 360 days to make a year. Although if you go to Nanjing, that as much as 2,500 years ago, the astronomers at Nanjing understood that a year was about 365 and a quarter days. They understood it was not exact. So they were the first ones to actually know that there was a non-integral shift. So they spent more time describing what it is rather than making it convenient.
So when did people realize, was it not till more modern times or more ancient times, that people realized that these weren't just lights in the sky, but they were actually objects out there?
Well, that's in some ways the notion of what those things were have varied, right? In terms of the concept that the Earth was a planet like other things up in the sky, that was a fairly late development. Although people like Giordano Bruno had more advanced thinking in that thing. Sadly, he was burnt at the stake to purify his soul because the church felt that the heresies he uttered were so evil that they needed to cure his soul of evil, and they burned him at the stake. But there there is this notion of what is a celestial object, and we'll see going on down here, debate about, is the sun different than the moon, different than the planets, different than the stars, and the notion of these being objects is actually comes up fairly late. Some people speculated, but as you'll see, we went from things where people said stuff is moving around the sky, but they're going in patterns, and we can kind of call these patterns certain cycles, and we can guess what sometimes happens. But the notion of what they are didn't develop until much later. I think, again, we talk about early stuff. There are ancient artifacts. There's the firmament models, the Babylonian cycles, the Chinese theories. It isn't until we get to Greek astronomy that we have some more advanced models about what they might actually, where they might be, and what they might be doing. Why are certain objects going against the flow of the stars, the firmament?
What about the realization that that people in very distant lands from each other see different stars, and
we'll get to that. We'll see
at different times.
Of that
did that require like writing, or did that exist, do you think, before writing?
That came in a little bit later, and particularly the Greeks were some of the first that we know of to talk about how the sky is, because they were some of the first to begin to build models of what the Earth was like, and the shape of the Earth, and the size of the Earth. But we'll get to that in a moment. But those are things that come about, right? Go ahead.
Yeah, that reminds me of a question. Was it just the northern hemisphere doing these things, or anybody from the southern hemisphere doing this too?
Same thing, right? I mean, and people that cross, right? They're the notion that there were people that were equatorial, moved around. There were along the African coast, there were people that went up and down the African coast that understood about things. It one of the things we'll get into it later of Islamic astronomy had a major impact on navigation, where the command to pray towards Mecca was not Mecca is generally that direction, so we'll pray in that direction. Knowing where it was and being able to pray that direction was a critical thing, and that led to a lot of navigation stuff. It isn't until the Islamic scholars taught in places like the so-called Portuguese school of navigation, where Moors coming into Europe and teaching a bunch of ignorant priests and explorers how the world actually was, and so that the concepts, however, of the stars are different was something that the astrolabe. But again, we're getting ahead of ourselves. We need to talk about I think a significant development of Greek astronomy that begin to have these kind of Greek thinkers that began to notice the periodic fashion of the solar system. They then regarded it as the universe, right? And began to they were puzzled about retrograde, that they would watch much more carefully these wanderers, they called wandering things, the planets that wandered in amongst the stars and firmament. And they noticed that it wasn't just merely that they were moving in one direction, but they would sometimes go to a spot, stop, go backwards for a bit, stop, and then go forward again. These retrograde things, these zigzag things that they saw going out there. And they were puzzled by that, right? So we began to see with the Greeks, I mean, as early as like 600 BCE, that they began to look at these wandering stars as are taken as so one of the models was that they were deities, right? They were important beings that but again, purely speculative. And so we have something like, for example, Thales of Matthias had predicted allegedly predicted a solar eclipse of 568 BCE. And we have people like Parmenides that claimed that the universe was spherical and moonlight was a reflection of sunlight. Some people say, well, that's kind of wacky, right? The moon, good people thought the moon shines in its own light. And he said, no, it's reflecting light. And in particular, his argument was, well, when the moon's partially lit, you're showing you the side that's being reflected from the sun, right? That's why it's dark here and light there, right? So he was actually, and then
did he also observe that when you can actually see the dark side, I don't mean the far side, I mean the dark side of the moon on particularly dark nights with good conditions, because you can see because of star shine on, and possibly a little bit of earth shine, I don't know.
Yeah. And he argued about, he built a fire next to a monument, a tower monument, and said, look, at night, and said, look, see this side over here, you can see it's lit. You go around the side, this other side, you can see it's there. It's much fainter because it's not reflecting the light of the fire. So that's what the moon's doing, right? He would basically would go people and say, look at this thing. The moon's doing the same kind of thing. But he was actually, there was this guy, I apologize for the pronunciation, Anaxagoras, who was the first one to consider the sun as a huge object. The sun is a major object. It wasn't just a wandering dot, part because you can see it's a half-degree blob. That he began to realize that this thing is hot and big, and the earth must be fiery. He thought, it's fiery things. So the earth had to be far away from it, otherwise we burnt up. He also suggested the moon would have been rocky, and therefore opaque, right? And it's a rocky thing that must be closer to the earth because it's not. First of all, he said it goes in front of the sun on occasion, so it has to be closer than the sun. And it's a rock; it has to be cooler towards the earth, so it must be smaller than the sun.
And you can also tell that it is opaque because it blocks stars.
Yes, and also occults Saturn, Jupiter, Mars, that sort of thing. Now he thought, when people asked, what do you think our comets are? He said, well, they're probably planets knocking things out of the sky. Planet bumps into something and knocks out of the sky and goes, right?
That's actually not a bad take, in my opinion.
Yeah, and so he was one of the people that sort of said, well, we can do these experiments and see similar things. So he was speculating that the stuff going on in there must be similar. That was a bold move because other people were saying, back even just a century earlier, people were saying, well, these are gods doing stuff in the sky, or God made it, and so forth. It coming in this again. Anaximander cosmology around 560 BCE was the first known person to conceive of a mechanical model of the world. By that meaning that these things weren't just up there, but they were. His model: Earth floats at the very center of an infinite universe, not supported by anything. He said the Earth is in the center, not supporting anything. It's just the center of this infinite universe, and that it has a shape of a cylinder that about 1/3 of the diameter, and the top forms. So he had an odd model with it, but he had this notion of saying, well, you got this separation between hot and cold, this ball of flame. He said appeared that the Earth, surrounded the Earth like a bark on a tree. This ball broke apart and from the rest of the universe, and you end up with the consequence of the sun was a fire that one could see through. There was a hole in one of these spheres, and the sun was this hole in this sphere that you could see the fire coming through. And so an eclipse, there's another hole for, and it said that the sun had this sort of this same size of the Earth, the farthest wheel. An eclipse corresponded to when there was an occlusion of that hole. And diameter hole, he said, was 27 times that of Earth. So his notion was that the sun was 27 to 28 times, depending on which excuse he gave, and that the planets. His thing, the sun was the farthest, and then there was about 28 Earth spots away, and Earth diameters away, or Earth cylinders away, and that the moon was 8 to 19, and the stars were 9 to 10. His argument was the stars are not as bright, so they're not as hot. They're closer. And so I say again, his model, the planets, the stars were closest, and then you had the planet, and then you had the moon, and then you had the sun, and so forth.
I might be misremembering, but didn't some people think that the sun was smaller than the Earth for a while?
Yeah, there are those models. Again, plenty of models are there, but he on the other hand, unlike the previous guy we talked about, he's sort of like saying, well, the sun's hot, so it must be blah blah blah, and there must be this, right? He went off on all these tangents. The notion of testing that, or whether it was rational, really wasn't in there. He was describing it. Pythagoras, another one. Pythagoras, although a lot of Pythagorean stuff is really corresponds to many of his students and followers on, but the Pythagoras system believed the motion of the planets was caused by an out of sight fire at the center of the universe. Now, the center of the universe was not the sun, right? He said there's a celestial fire at the center of the universe, and that the Earth's inhabited side was always opposite the celestial fire, which is why you couldn't see it. He said, "Okay, got this little," and again, there's a diagram there that I think might show it.
I can show it. I found a diagram.
Yeah.
Let me.
And so he had a thing where, okay, so you have this celestial fire at the center of the universe, and the side of the Earth, the inhabited side, was opposite of the fire. So we never saw it. We never saw the thing. Right? And there was also, so the Earth went around the center of fire every 24 hours.
Yeah, so it goes around the center of fire every 24 hours, and the sun goes around once a year.
Yes, and there was also there was this anti-Earth thing that was on the other side, because in part because they said the number 10 they said was perfection, and so they had to have a 10th body, right? You say, well, what do you mean a body? Well, you had the Earth, the Moon, the Sun, Mercury, Venus, Mars, Jupiter, Saturn. You had the celestial fire, and so 10 is a good, nice, perfect number in the universe. It's perfect, so we have to have a 10th body, right? This counter Earth there. Again, we're talking about one of the things is that, well, the universe must be like this. This is what we want the universe to be like. This is a universe like this is good, right? Not even really trying to test what it is or measure what it is, saying the universe must be like this.
So this diagram shows that I don't know how to pronounce that. Antikython, something like that. That this body had a smaller orbit, but it
stayed.
did it orbit at 24 hours just so that it would always be right out of reach?
Yes. Yeah. And the reason why they said they had it is because 10 was a nice number. They liked 10. And 9 was considered to be not so nice, right? Again, we're talking about notions saying, well, the universe must be nice, and 10's a nicer number than 9, so there must be 10 things, so there must be a thing we never see, which is on the other side of the Earth, on the other direction of the Earth, opposite of the Earth. That's why we never see it. Excuse, right? It's one of those sad things where there was a bunch of people that said, this is what the universe should be. This is a proper universe should be like this, right?
Proper universe.
A good universe. This is what the universe must be like. Now, and it's hard to say whether people like Pythagorean wondered about this and his students took off like a colt, or whether they believed or not. That's a debate there. Plato came around and wrote his thesis and claimed that there were circles and spheres. Circles and spheres were the preferred shape of the universe, right? The universe liked circles and spheres. So there's a this is where you start to get these sort of centric models, these shells. And so the geocentric model, and if you find one of those geocentric models of the solar system, I think there is one. I think there is one in there. We have that set, but the epistemology, you had this there's this primacy of the motion of sameness that left undivided. So he divided the motion of difference of 6 parts to have 7
this one?
Yes. Yeah. Well, that's one of them. Probably there's another one that's sort of his geocentric model.
This is Ptolemy, though.
No, you went early on with Platonic.
We don't have any other diagrams before that.
But anyway, so he arranged to have these celestial orbs in order, and his order was Moon, Sun, Venus, Mercury, Mars, Jupiter, Saturn, and the fixed stars. So I can.
Okay, so it was not this. So you said Moon, Sun.
Moon, Sun.
Okay. Because this is different.
Venus, Mercury, and then Mars, Jupiter, Saturn, and fixed stars. So again, this is one of those models things. He didn't actually explain the motion. He just said there's spheres, right? Things are going around in these spheres. And so his were like, his thing is like, well, spheres and circles are the preferred shape of the universe, so the universe must be filled with spheres and circles. So it wasn't. You got a student of Plato, Eudoxus, that around 75, or actually, no, it's around 380 BCE, introduced the technique to describe the motion of the planets. We called it a method of exhaustion, where he reasoned that since the distance of the stars and the moon and the sun were all the known planets did not appear to be changing, he said they must be fixed on a sphere whose bodies move around on that sphere, but with a constant radius. The Earth was at the center. But again, he said, well, you look at these objects and they don't change size, so the Earth must be in the center of this spherical thing, and they must be going around in a circle. So the distance to the Earth is constant. Was his he tried to explain sort of the by saying, well, because they're constant, they must be going around. The Earth must be the center, and they must be going around in these sort of spheres. And so they have these sort of invisible spheres, each one of them rotating around its own different axis at different places. So he actually had, his model had about 27 of these spheres, each sphere explaining observable motion of an object, right? And so he had, for example, a sphere of the fixed stars, which explain that sphere went around Earth daily. So that was the stars going around once a day. He assigned the spheres of both the sun and the moon as the first sphere moving in a manner, same manner as the fixed stars. And the second sphere explains the movement of the sun, Earth on the ecliptic plane. So that was his third sphere was supposed to be sort of longitudinally inclined circle to explain the sort of the longitudinal motion, that the fact that the moon and sun went up and down longitude wise. And he had 4 spheres assigned to Mercury, Venus, Mars, Jupiter, and then he had another one for Saturn. He said that they moved like the sun, but at a different rate, right? He basically expressed this as a purely mathematical concept, that the spheres have to exist, but he didn't say that the spheres exist. He just said mathematically they're like spheres. They must be going in spherical positions, right? He was kind of almost like saying, well, there are orbits. I don't know there really are spheres there, but that's the model that it looks like. But there were other people like Aristotle that modified his model to say that the spheres were material and crystalline, not just concepts, right? Aristotle actually wanted it to be there. And he started coming up with spheres, rolling around on spheres to try to explain retrograde. And he had up to like 55 at some point spheres of these things rolling around things, and kind of as crazy, really sort of crazy. They're not sure how many spheres they ended up being because they kept inventing spheres to explain certain motions in the sky. Just, if you needed how it come it did this, well, there's more spheres rolling and things around. It was kind of the early, not quite epicycles, but it was kind of that heading in that direction. And so it was, again, whereas Eudoxus said mathematically as if they're spherical things, Aristotle said, well, no, they're real. They're material. They're crystalline. And then they started spheres rolling around on spheres and blah, 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 and just became crazier and crazier because they said, well, it must be spheres because spheres are nice. They like spheres. They didn't want a universe to be icky. We move forward about 330 BC. So again, Aristotle, we're talking about around 350 BCE. About 330 BCE, Heracles was somebody said that it rotates the Earth the Earth rotated on its own axis from west to east once every 24 hours. So he was said, no, the Earth isn't fixed. The Earth actually spins. And he said, the stars are fixed and the Earth is spinning.
So at this point, most people knew that the Earth was round at this point.
Well, they were speculating. We'll get to that in a point. But this is one of the things. But his notion that if the Earth is spinning and circles and spheres are nice, the world must be a sphere because it spins. And again, they could come with things and not explain stuff. People say, well, how come we don't feel the wind and blah, blah, blah. And they didn't have to explain everything. They just said, this is what it should be. He explained the Earth moves while the sun stays still. Now there's dispute about that, but so this is said that he proposed these irregular movements that could explain if the Earth moves and the sun stays still within the cosmos. Again, the Earth was still the center, but the Earth spins. So the sun's over there, and the Earth spins around, and that's why the sun appears to move, but the sun stays the same spot.
So the sun that go around the Earth, the Earth just rotated in this made it look like it.
Yes. And then he had to think. So then you have people that began to around 280 BCE, I believe, was the first definite discussion about the possibility of a heliocentric cosmos. Not quite, but they looked at the Earth's shadow cast during a lunar eclipse, and they sort of looked at the curve of that shadow and said the Earth must be, the moon's orbital radius must be 60 Earth radii.
Which is basically correct.
Yes. I mean, they were doing geometric proportions, right? They were saying that the Earth is casting a shadow from the sun, and the arc of the Earth has a curve around the moon when it's going into a lunar eclipse at this shape. So therefore, the moon must be 60 times farther away, which is actually not bad of a set. Now he attempted, and again, now we're seeing somebody who is not saying, "Oh, a good universe must be like this." He's actually doing measurements and saying, "This is a model that shows the ratio between the size of the Earth and the distance." He tried to do that for the sun, and I think I have to give him credit for is that he found that he didn't have sufficient data to assert the distance to the sun. But he said, I have data enough to assert that the sun must be bigger than the Earth, and therefore must be farther away than the moon. And therefore there was this, he didn't know how far it was, but there's this ratio where you look out from a point of view of projection, and you'd see the moon subtend a half degree, and somewhat farther back, much farther back, was the sun. So following on that thing, they actually, there are other people that tried to use some of his ideas and measurements, people like Archimedes, to suggest that the sun was about, that given where the sun is and the stars must be around 2 light years away. Was his sort of things, and so it was an interesting thing. His views weren't widely adopted, but it was an interesting set of someone saying, let's try to do some measurements and see if we can figure this out rather than just assume. You had other people started to look at this notion of this apparent retrograde, right? They come back around 210 BCE. Apollonius was looking at these things and seeing, hey, you could explain retrograde if you have a circle rolling around on the circle. People like circles, so I said that's pretty good. And if you have a circle that rolls around on a circle, it'll have this back-forward thing. There, do we have a diagram of that? No, we don't.
No, I can't find. I only found so many diagrams.
But because I wish I could hand these diagrams to you. Anyway, how can I do this? Can I give you a link? I can give you a link.
You can also
of the diagram you can show.
I don't know.
We do that. We would try to do a screen share, or
well, either that or share the link and we can screen share.
Okay, I'll share the link through what means. Sorry, we should have gotten this ahead of time. Share the link through how? How do you want me to send you the link?
Either through Discord or the private chat.
Okay, let me do it through Discord here. Apologize, folks. Try that. So you had people who were measuring stuff. I want to mention, by the way, there's this link too you should put out beforehand. I'll give you this link. This is an important link, an important text. So I'm going to put this into Discord as well. So that second link I had, that you see the diagram. Can you display that second diagram? Hello?
Yeah, I can. I found it on this one.
1 second.
Yeah.
Yes. So this is example again where they're talking about measuring the size of the lunar orbit relative to the size of the Earth, and having people who began to understand the size of the Earth. They knew the sun was bigger. They also, I give them credit that they tried to measure the size of the sun through experiments and determined they didn't have enough data, but they just said the sun has to be further back and bigger. The other one, if you go back to Apollonius and that epicycles thing.
I don't know what you're asking of me.
That's the second. That was the second link. I'm sorry.
You just sent me images. I can't. I don't know how to show. Oh, here. Oh, okay. I found it.
Yes. So in this measuring thing, and they said, okay, that's nice, but these wandering planets have this retrograde. What's this retrograde stuff? If you got these dust on a sphere, and they said, well, if it's a sphere rolling around on a sphere, then you get these retrograde cycles, right? When it goes from 2 to 3, it appears to go backwards. And said that's why the things go forward backwards. It's a rolling of a thing around a thing, right? And this is where you got to be all these spheres and all these stuff. People said, hey, I like that. That explains stuff. And it was now one of the things that also happened around that time, around 150 BCE, Hipparchus uses parallax to determine this distance to the moon. Basically, two people in different spots with a known distance from the Earth seeing the moon move, and he estimated, they didn't use this word, but he estimated that because around 200 BCE, Greeks determined the radius of the Earth was around 6,400. The radius was around 6,400 kilometers, which is not bad of a size. And then Hipparchus used this stuff to say, well, then the moon must be around 380,000 kilometers, which is also not bad for stuff. Again, they're measuring things, and they're saying we can do these ratios. It's just not just a bunch of what it might be like. Apollonius said, well, you can get retrogrades by having that wheel rolling around on a wheel, cycles within cycles. And that's something that Ptolemy took off, and his thing was these epicycles, right? That's what happened. In fact, he'd even have cycles on cycles on cycles, right? That it's not just the first wheel rolling around the second wheel, but there's a third wheel rolling around the second wheel to give even more complex motions. And so we had basically all these spheres rolling around each other to explain the apparent motion of the planets. And that kind of became the dominant model. This geocentric model lasted almost for 1,500 years, where people said, well, that must be the case, right? Because the epicycles were kind of explained, and rolling things and so forth. They didn't dispute this Earth-size stuff or the Earth-moon distance thing. They didn't dispute that the sun must be farther away. They didn't know how far it was. But this epicycle said that explains things, and it circles, so it's nice.
they're not like wrong. You can make that work. The thing is, you can make anything work with that model. For example, I found this GIF of how you trace out a bird with I don't know how many different circles
Yes.
are used here, but there's a red spot here that's tracing out this flying bird shape, and all of these are circles.
Yes, and again, the notion of circle spheres are the universe likes that. It shows purity. We can't have the universe being ugly. So
is that the Falcon constellation?
So I want to. So the Ptolemy's thing with the epicycles became the dominant stuff. Again, we saw some things about maybe the Earth is spinning and the sun is there, and that sort of things kind of dropped off and dropped out of favor with this Ptolemy stuff. Sat around for a while. In fact, there were religious people that said that he was so right, he must have been divinely inspired, and they didn't appreciate if somebody challenged him. Now there were modified geocentric models that showed around like 420 AD. Capella described a model where the Earth is at rest at the center of the universe, circled by the moon, and the sun has planets Mercury and Venus circling the sun. So it was that geocentric model, but now Venus and Mercury orbit the sun. So you have the Earth in the center, and then you have the moon, and then you have the sun with Venus and Mercury going around it, and then you have Mars, Jupiter, Saturn, and the stars.
So was at this point Saturn was the furthest planet we could see with our own eyes?
No, the stars. The stars were even farther.
Right. But we didn't know about the other planets yet. Uranus,
correct,
and Neptune.
Yep. Again, we're talking about 420 AD type of thing as this model. So they said, it's kind of Ptolemy's, but a little bit modified. You can have epicycles on top of that, but it's kind of explained. And this is the first time where somebody said, there's something orbiting, not the Earth. And that's what they explain about the fact that Venus and Mercury were never too far away from the sun, because they're orbiting the sun, not Earth, which was kind of an interesting thing. Now, so let's move forward to Islamic astronomy and the Golden Age and area, particularly around areas of Baghdad, that were looking at Ptolemy's work and saying, there's a more accurate measurements need to be taken. And so he had kind of his doubts of stuff, especially because there's a guy, Ibn
So this was before the Mongols burned it down.
This is 1021 AD.
Burned all the books.
And so Ibn al-Athan sort of adjusted model, because he said, he wrote a book, which Arabic translation is Doubts About Ptolemy, and he claimed that the epicycles were actually are actually inclined planes, not flat, and that the orbits of these planets must not be in the same plane; they must be off each other, right? So he was able to get better Ptolemy's fit by not insisting that all the planets have the same orbit, the same orbital plane, right? And he said, it's very obvious the moon is around 5 degrees off from the rest of stuff, right? And that the other planets are slightly off as well. And if you allow them to be in slightly different planes, you can get a better fit with fewer epicycles. And if you explained why, he said, well, corruption and so forth and decay has caused it. It was nice and aligned, but people did bad things, and knocked out of alignment. There was actually, and so there were, interesting enough, there were, Copernicus arrived at the same conclusion in the 16th century and attempted to try to resolve Ptolemy's inconsistent lunar theory by applying a double epicycle to the moon's motion. But people said, so the question was that uglier? Was the fact that each one had its own plane slightly different? Was that uglier than a whole bunch of epicycles? Right? They still had epicycles, but they didn't need as many to account for the apparent orbital inclination. Around the same time as well, back in China, Shen Kua, a Chinese scholar in applied mathematics, rejected circular planetary motion and submitted that he had a term he called willow leaf, where the planets had a circular orbit but encounters another smaller circular orbit with inside it such that it returns back to its real, that he had distorted circles. He was kind of close to ellipses, but not quite. He was saying that a circle distorted another circle. So you had circles squished. Again, it's hard to describe. His description of stuff without formulae was more poetic, but people can interpret it as saying that he was suggesting that maybe not everything is a nice circle. Maybe these circles have been distorted a bit.
So it sounds like epicycles, but with less specificity.
Yes, or the fact, again, if you go back to what Ibn Hatham suggested, he said if you abandon all of the objects orbit on the same plane and instead allow their planes to be slightly different, you don't need as many epicycles to get a reasonable prediction of where the objects are. So that's a kind of interesting thing. Again, these are things, but they didn't necessarily catch on. There were people suggesting there might be better models. So let's, any questions before we move on to the Renaissance and Copernicus and heliocentric models?
So this is all before we had telescopes. This is all visual, our own visual.
Yes. Yes. Even we're going to go through several people as well before we get to telescopic measurements.
Any questions in chat, people?
Do you know of any diagrams for this Shen Kua willow leaf? Well, I'm looking for one, but I don't see one immediately.
I mean, the diagrams I know of are text. He wrote text and poetry, and he had mathematical diagrams, not models of things. He had a number of stuff. He was a pretty smart dude. He did a lot of really fascinating, approaches to mathematics. And again, I think he was close to ellipses. If he only had discovered conical projection, he probably would have seen ellipses as being a thing. But he was close there, but not quite. But still, the fact that he was challenging, maybe something isn't so circular. Maybe there is he said this term willow leaf, when a planet has a circular orbit but encounters another smaller circular orbit inside it. It's like this other orbit pushes the circle out. Right?
I think we have a question.
Sure.
Maybe.
What was the question?
It's on the screen. Eddie McCoy asks or states, I think planets with less mass might orbit slower. They do not. The but we're not quite to the reason why yet. And in fact, I mean, the least massive planet in the solar system is Mercury, and it has the fastest orbital velocity because it's the closest.
Yeah. Although you might say that again, if you're also if you have a geophysical model of a planet, then a planet like Ceres is another one versus
Yeah.
so mass a planet's orbital period is really kind of it's not a function of mass. That is, the bigger mass somehow slings it out farther. There's a distance period relationship that we'll get to in a moment.
Yeah.
So let's talk about Copernicus, right? Copernicus had a 6-degree model where, he's thinking about Ptolemy, and he says, it's a lot easier if you make the sun the center. You need even fewer epicycles in order to do this thing. In fact, his Copernican model, and I'll give you a link to one of those. This is a famous diagram in one of his books. If I can get the let me go here. Apologize, folks. To there. If you pick up that diagram.
Yeah, I've got it.
That's a famous one there. So what we're seeing here is that he sort of said, you're working really hard to try to do all these wacky epicycles, and you can get away with a lot fewer stuff if you don't insist that the Earth is the center. So he had the sun, then Mercury, Venus. He had Earth with the moon around Earth, Mars, Jupiter, Saturn, and then the firmament, the stars.
So this is Earth, and this is the moon around her.
Yeah. So he basically said, you have a lot easier thing if you have these circles, and he implied, actually, an interesting thing. This is probably the first time that someone definitively said Earth is just a planet. Before the question was asked, when do people think? Well, the Copernican model, one of the things it did was to say Earth is also a planet.
Gasp.
And now the problem with the Copernican model, so the Copernican model was simpler in model, but didn't do well in terms of predicting where things were. And so we move from Copernicus, 16th century, to Tycho Brahe, and in 1588 published his own system, and had a blend between Ptolemy's classic geocentric model and Copernicus' heliocentric model, in which the sun and the moon revolve around Earth in the center of the universe. Other planets revolve around the sun. Right? Again, it's a little bit more complex than that. I'll show you a diagram.
I found a diagram on the Wikipedia.
All right. Okay.
Is it this one?
Yeah. So here's a model where Copernicus is saying, okay, Tycho is saying, and I'll explain why. He said, you can get Ptolemy things with these epicycles, but let's have it be kind of geocentric, but let's have epicycles, because one of the things that that Tycho Brahe did was he was a observationalist. He measured positions of stars and planets. He's said to have extraordinary visual acuity and could reliably measure a position of an object in the sky with an arc minute. That is 1/60th of a degree. And he was he very demanding of assistants who were also taking measurements. He had these giant sort of quadrant protractors where he would, again, we're talking about pre-telescope. We'd have kind of like think of like a gun sight with an angle measurement. They would measure the angle so he could basically fix the position of a planet, a star, and get it to within an arc minute of its position. And only one of his students could reliably please his ability, and that was Johannes Kepler. We'll talk about in just a moment. But Tycho is trying to say, okay, there's this thing about Copernicus. The problem with Copernicus was that it had a simpler model. The heliocentric was simpler. The Copernicus model did a worse job of predicting where planets were than Ptolemy. Because again, epicycle, you can do anything you want. You can curve fit, right? And so people think the Copernican system was this revolutionary thing. Well, no, there was valid mathematical scientific objection to Copernicus's model, that circular thing, because it didn't do as good a job as Ptolemy. And so Tycho tried to say, well, there's something to be said for it, particularly having Mercury and Venus around the sun and having the Earth go around the sun, but we can have these epicycles on top. So he kind of had this hybrid thing.
But everything is still circles, right, in this model?
Yes. And it isn't until we get to Kepler.
What degree of freedom, though, is it that this model has that Copernicus did not have that allowed it to do better? I guess you have an extra flexibility. There must be more degrees of freedom in order for the model to.
Yeah, you can see if I say that the moon going around the Earth and the Earth rolling and having it's rolling within the celestial sphere. So you have sort of the Earth is shown, the Earth has a rolling thing and the sun has a rolling thing around it that does some rolling and gives you a little bit of these orbits that and again the sphere of stars also rotates, right? So that outer edge of the stars is rotating, and the thing inside is rolling around the other thing.
Okay, so maybe you get well, I guess you might have some freedom in the distance between the Earth and I guess you have all of the distances, and then you have the velocities that they go around.
Yes. And so what Tycho is trying to do was to explain, to give a Copernican-like model that gave you a more accurate position of the planets. Because again, Copernican did worse job than Ptolemy's. Because Copernican wanted to have first of all, the Copernican one was all the planets were in the same plane. They're all circular orbits. And that kind of fails. And that was one of the objections. A valid scientific objection is, there's a GIF, animated GIF I wanted to show, which is really going to celebrate what Kepler did. Now, Kepler, a student of Tycho who could do measurements as good as Tycho, extended Tycho after he died his incredible measurement of these things, and he noticed there was an inconsistency in the heliocentric model where the sun was exactly at the center. So he said, and Kepler spent a lot of time trying to have these like a triangle within a square within a pentagram, so forth. These geometric things to try to come up with some rationalization about the possible distances between these spheres. And he was determined to have some geometric thing because he said the universe made by God must have some rational thing, right? The story, one of the story goes is that he's trying to get these things to fit, and trying to figure out these. Again, if you inscribe a like a pentagram around a circle, and you describe a circle around that, and describe a hexagon around that. This gives you the distance of these circles. He said there must be these reasons why these things are there to try to figure out a better fit. But of course, remember, he had plenty of data from both Tycho and his model of accurate position, so he knew where things were over a long period of time quite accurately. He was trying to fit things and was failing. And I remember that the story goes that he was kind of, it was time for him to eat something. So he put his work aside, went over to a side table to eat some lunch, but kept thinking, look back at his diagram, and he saw the circle at a angle, and he saw that it was an ellipse. And that was the light bulb flashing, saying, ellipses are just these kind of tilted circles. They are nice circular things. We just they have, rather being rejected as being bad things, they were projections. He's basically doing the conical sphere sort of stuff. Some of the projection stuff to see, and it was that ellipse that said, they can be elliptical slightly, because you've got these things that kind of like the projections on these planes that we're seeing them on the side. And that's when he started looking at the data, try to fit the data back in. And so he came up with his 3 laws, right? He found a really good fit on his data. And he said the first one was all planets orbit the sun in elliptical orbits, not circular. He said ellipses are perfectly nice, beautiful things. Don't discount them because they're slightly squished. They're this projection thing, right? And he said the other thing he said was that he found was that the radius vector, if you draw that line, so you look at this object and draw the line between the object and the sun, that line sweeps across equal area over equal periods. He was trying to actually divide up the where he's trying to plot where the object would be fitting the data on the sky, and notice that the area of those wedges, see a dot, sun, dot, right? Imagine a wedge there. Those wedges all have the same area. That is, another thing is that a planet sweeps, a line between the planet and the sun sweeps out equal area over equal periods of time.
Yeah. So I presumably in this diagram here, the little black points are sampling the position at equal intervals of time. Yep. And if you draw the section of the circle from between two, or ellipse rather, sorry, between two black points and the sun out, which is at one of the focuses, which that's the thing in an ellipse, then the area of each one of these triangles is equal, which means that this body has to be going much more rapidly when it's near the sun.
Yes. And so there's probably a better diagram. I will give you, here's a link. Probably. Here's a link that you might, I'll give you a link to this diagram. One of the things that my colleague had, that there is a diagram here. I'm putting it into Discord here. Take a look at this diagram. Okay. It's got a white.
I can.
Okay, there it is. Yeah, there you go. So you see how A1 and A2, the two sets there, those have the same area. A1 and A2 shaded have the same area. The sun's at the center. The planet is the purple ellipse thing, and the time it takes for the planet to cross the arc of A1 is the same time as A2. A1 and A2 have the same area. And this came about because Kepler was basically trying to plot where was how did the planet, he said the planet didn't just have a same angle around the sun. There must be some geometric reason why it was going seemingly faster and slower. And then he realized it's the same areas swept out. The line between the sun at the focus and so forth was the same area. So that's Kepler's his second law. I said this vector is that swept out covers equal area at equal times. The third thing, he's again deduced by just sheer mathematical brute force, was that the square of the period, how long it takes to go around the sun, is proportional to the cube of the average distance.
Yeah, it's commonly called the square cube law,
Yes.
and we express it nowadays in this, where here A is the radius. A is, in this case, is I think the semi-major axis.
Yes.
Since it's ellipses don't have one radius; they have a bunch of them, but you express them in terms of sort of their distance, the fat side, the small side. Yeah. And so that ratio is always the same when it's orbiting around an object with a given mass, and all of the planets are all orbiting the sun. This does not hold for looking at comparing the orbit of the moon around the Earth to the Earth around the sun.
Yes, they have to run the same center of mass.
Yes.
So it explains that why does Mars go around, take this around at this distance, and Jupiter this time of this distance. Basically, it's a distance to the center of mass orbital period, right? This square cube ratio is independent of the mass of the object.
Yes. Yes, of the small orbiting object.
Yes. So and again, we start with Tycho, who wanted to have an accurate map of the heavens and was so anal retentive, he wanted to have really precise data. And then Kepler extending his stuff to have enough data to then be trying to fit the curve. He kept looking for mathematical explanations, stumbled upon ellipses, and then trying to figure out this fast, slow stuff, discovered this second law, which is the sweeping area, and the third thing, which was the square of the period, proportional to the cube of the average distance. What do you mean by average distance? Well, what Kepler said is you could have a planet that was perfectly circular that would orbit the same speed as this elliptical thing. So that's what he called the average distance, would be his original solution. Now, again, Kepler asserted these things. Go ahead.
Is it the average distance, or is it? I think it's so. I think what it is like, so for this purple ellipse here, I think it's the quantity A1, which is from the center to the distance from the center to the furthest point, and there are two furthest points.
Again, I'm describing it as Kepler stated it.
Yeah.
Now it's not until you have Newton, who came and said, if you have an inverse gravitational field, you get ellipses and they have these properties, right? He applied the calculus to say why. Remember, what Kepler was doing, Kepler was an experimentalist and observationist who said, we're going to observe these planets accurately. We're going to build up tables, They give you a geometric model, not what it is, how to predict where they are. And so Kepler said they're not in the same plane. They're not circles, they're ellipses. The sun is at the focus of one of the ellipses, and they have this radius equal period stuff and this cube square proportion. Now we call the notion that if you took an elliptical orbit and you said what circular orbit has the same period as the ellipse, that's the same major axis, what you would call it, right? But I'm referring to how Kepler described it. And the thing about Kepler stuff is that his model became super accurate, right? Again, the best people could do pre-telescope was around 1 arc minute, and he could nail it every time where things were. It was none of this, and it didn't need all these epicycles. It didn't need all this stuff. You had the sun at the focus of an ellipse, of the ellipses. The ellipses not being the same plane, the ellipses having these geometric properties, and the orbits having these geometric properties. And to Kepler, that was satisfactory, and it was accurate, and it didn't need crazy 55 spheres and rolling pulley things and so forth. It was a fairly straightforward, and he allowed himself to see the beauty of ellipses and not insist that old Greek idea of the universe likes spheres and circles. No, the universe likes ellipses and spheroids, and and it does things it doesn't like either. So you can't count on it. He had essentially, so really had, one of the things he had was, once he had a distance of one planet, you could tell the ratio of how far Saturn was from the sun compared with Mars because of the periods. And so he began to build a model that was mathematically sound, not it must look like this and it must have these spheres. Now, we need to move forward. Again, so now we're talking about an observationalist applying mathematical models, seeing a more advanced thing. We want to jump to Galileo, who did not invent a telescope, but he was one of the early pioneers of using the telescope to look in the sky.
He also built, I think he built his own, and he did them better than they had been before, is my understanding. I could be wrong.
Yes, but I've looked through 2 of Galileo's telescopes. And I'll tell you, it's amazing you could see anything out of them, right? Again, if that's all you had, it was pretty good. His first telescope in Latin is the lens is broken, and in Latin he wrote on the end of it, "I did this." Right? So he said, "I dropped it. Sorry."
Now, did he go from looking at ships to the stars, or from the stars to the ships?
He was employed to look at ships to game the prices of commodities for the Vinci brothers. To play, he was playing fast and loose with commodity markets, using telescopes to look at, determine the flag of a ship coming forward. Knowing its registry, they would then adjust prices, saying, "Okay, here's a ship. It belongs to Bishop so and so. It's carrying flax, and they want to buy wool. So we'll drop the price of this and raise the price of that, and profit."
That's pretty clever.
I mean, he now, it was sad because he stayed on Padua, where he was a professor, he was in a protected area from political forces, and he could have spent the rest of his life in relative comfort, but he ran into a number of problems. He was kind of a showman. He he was a big in making public spectacles, right? One of the things he did was, in Siena, the river there, he was teaching. He was a teacher of the ministry, children, and so he would ask them public, this public lecture. He said, um, uh, why to he threw a stone in the river and it sank. And said, why did that stone sink? The students kind of mumbled around, blah blah blah, and they said, well, it's heavy, right? It sinks to the bottom. And so he had on the side a cart covered with straw and sawdust that had been up in the Alps and grabbed a big chunk of ice. It had this ice that took like 3 men to lift, and they heaved it into the river, and the ice floated. And he said, students, explain that. This heavy thing that took 3 people to lift floats in the river, but the stone that I can toss in sinks. And he would pose these things there, and people loved to go to his sort of classes, his lectures, because he was a pretty big show person. And he loved to do experiments. One of his ill-fitting experiments was that he, during a dinner in Polonaise, and it was one of the cardinals was there. He turned to the cardinal. He held up a large, like grapefruit, and a small kind of a almost like a kumquat, right, type of thing, a small citrus thing, big and small. And he said to the cardinal, when I drop these, which will hit the table first? And the cardinal said, the grapefruit, having greater need to hit the table, will hit first. That is heavier. He thinks the cardinal said it's heavier, so that one will do. And so he let it go, and they went hit the table at the same time. And so he was trying to say, well, okay, explain this. The problem was he just said, one of the elders of the church, tell me what the church says. I did an experiment to test it, and the church was wrong. This is an important point. It's something that I blasted this bishop who tried to, at the Vatican, tried to explain otherwise. The church has not apologized. They have not pardoned Galileo. Well, they apologized for the way he was tried. His crime was that he actually dared test the church. He dared do an experiment. He dared to ask the cardinal to pronounce something and then show the cardinal was wrong. That was his crime that he still is guilty of, right? The church has not pardoned him. They still go with the stuff because of the stupid thing. But anyway, sorry to say that no, you don't get to do stuff. To this day, the middle finger bone of Galileo is curved and points at the Florence Science Academy, where he have his inclined planes, all this stuff. The middle finger points towards the Vatican. Basically, the accusing finger back there in part. So back to what did Galileo actually do? He used a telescope to begin to take observations, right? I can imagine that Tycho and Kepler would have loved to have used a telescope to begin to do these more accurate measurements, because what Galileo saw were a couple things. He saw phases of Venus. He saw Venus acting like the moon. He was able to magnify enough to see Venus move through phases just like the moon did. He saw objects moving around Jupiter like like the model said that Venus and Mercury must move around the sun. Basically, he saw things orbiting other things, right? And a number of things. And so he really pushed forward the notion of showing. By the time you get to things like you've got moon having the phase of Venus having crescent things like the moon, and moons around Jupiter, orbiting Jupiter, and so forth. You're in a solid, heliocentric model of the solar system. Now, when I had the privilege of helping measure the distance between the Earth and the sun. One of my colleagues was in Madagascar, and I was in Arcetri, Italy. And they had me use the balcony of the prison that the church put Galileo into, and it allowed him out once a week on this balcony for about an hour. And so we did the measurement of the transit of Venus from Galileo's balcony, just as a poetic thing, to do the measurement stuff. But so we now have a telescope that's giving further evidence of heliocentric-like model. We have Kepler, who's gotten some geometric and mathematical things as a possible model, but not really something about why. And we have to move to Newton. We have to move now into the so-called Age of Enlightenment, and Newton with his law of universal gravitation, and his F. The force is gravitational constant times the product of the masses divided by the radius squared. And then using calculus to show that if you have this inverse square force, you get ellipses. You have this inverse square where you get Kepler's laws. So Kepler's laws are not just fancy mathematical model, fancy mathematical fitting of data. There's a mathematical thing saying out of inverse square law you get ellipses, you get this stuff, right? Newton pretty much nailed it in terms of a rational explanation, not just the universe is probably like spheres, so let's go and assume that things are spheres. He said, no, let's talk about laws and principles backed up by data to why, right? Now, actually, I don't even know if the term solar system didn't actually come into the English language until 1704 with John Locke, who referred to the sun, the planets, and the comets as a whole. That was kind of the first time that word solar system applies. So we've been talking about the solar system models. The actual term in English didn't come until that time. But getting ahead of ourselves, so Newton gave us this mathematical description of inverse square law and then why it's up to the ellipse. We had people like Cassini and Richter establish the distance to the distance to the sun. Later on, people like Captain Cook and his voyages with other people around there to the transit of Venus to figure out the distance and stuff. So begin to get scales of things. We had Kepler's laws that give us ratios. We had gravitational constant to give us the actual distances and measure masses. We can measure the mass of the Earth, measure the mass of the sun, and predict things to a pretty good thing.
You need to know the gravitation. You need Cavendish though to do that,
yes,
right?
That's right. And you're right. 1798, I believe.
Yep, 1798.
Where he measured the actual gravitational constant. I mean, they had guesses as to what the gravitational mass was, but it wasn't until Cavendish actually gave it some precision. Not much.
They had some idea because they had some idea of how big the Earth is. Probably at that point they had a fairly decent idea of how big the Earth was.
Yes.
And had a not horrific idea of how dense it was.
Yeah.
So you could get it to within an order of magnitude.
Yeah. And remember, the meter was described as 1/10,000,000th the distance between the equator and the North Pole. Right? That was the original definition. So they had a concept refined off of the Greeks, the same sort of thing that the Greeks did in terms of measuring stuff. A little bit more accuracy. But Cavendish started applying some precision to the gravitational constant.
Okay, real fast. You mentioned Newton a while ago. Did his theory of gravity or laws of gravity have anything to do with how we observe the orbits of planets nowadays?
To practical sense, yes, when you don't get extreme weirdnesses, when you're not
Yeah.
having neutron stars and warp space and so forth, when you're dealing with a lot more, let's call it terrestrial things, and you're not dealing with hyper precision. You don't,
Yeah,
you
yeah.
don't want, yeah. So if you talk about that day, it was pretty good. Now
it took a long time for any error with the Newtonian model to become apparent.
yes.
And
Yeah.
it really only it required hundreds of years of observations of Mercury to notice that it wasn't quite in the right spot
Yeah.
as it should have been according to this model.
Now, before we get ourselves on there,
Yeah.
we have to also stop. Certainly Cavendish gave us some better precision on the gravitational constant. And then we had his telescopic observations around the moons of Jupiter and Saturn and the ring system. But Halley was the one who kind of asserted that comets were actually objects. They just had highly eccentric orbits, right? A comet was not just this flying across the sky, but it was actually in an elliptical orbit. And Halley looked over records and noticed these great comets coming at a certain kind of period with a couple of gaps and thought there must be something that has about an 86-year period that must be this comet. And so what we call Halley's Comet, Halley never saw. He never lived to see the return. But he said, given it's this object must be going on an ellipse, and given the observations, it shows up here, here, and here. So we will see a new comet in 1758, and I believe it was.
Apparently, he said it would be in 1757, but it was perturbed by Jupiter,
that's right.
as Jupiter is wont to do, because Jupiter is really big.
Yep.
But it showed up in 1758.
Yeah, and it was, and you could argue saying it was late 1757 or 58. It wasn't too far off, but interference actually slowed the return actually about 618 days. Yet the same time is this first time in history a comet was anticipated and found. Now, another thing you have to say is around that time the same, this notion of you've got people begin to measure the ratios of the planets, but you had people like Titus and Bode who came up with sort of a progression about why you have these distances. Why are the question is, okay, we measure the distance of the planets to the sun, their seeing major axis, their mean orbit distance. But why are those distances? And so there was a sort of numerical progression, which is not quite correct, but it the reason why that Titus rule sort of works is that it has to do with how accretion disks are formed and how it sweeps out stuff. But it said, hey, you got this gap between Mars and Jupiter where this numeric regression should suggest there should be a planet. And of course, 1801, Sirius was discovered. And so it said, there's a missing planet. Kind of small, but then of course, they found one in 1802, 1803, blah, 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 and it sort of, by 1845, you had people that discovered a fifth body between Mars and Jupiter. It became notion that this zone wasn't a planet, but a whole bunch of rocks. We were kind of curious to say, okay, we have a zone that could have been a planet from a regression point of view, but wasn't. Now, we have another problem that occurred is that Boulevard detected irregular orbits of Uranus in around 1821. Uranus was discovered by Herschel in 1781. By 1821, telescopic measurements showed that the Uranus was not quite where it should be. And so, people said, okay, Newton stuff doesn't really work at this. Again, we're talking about really fine details, but now we have telescopes and precision enough that we can say that Uranus isn't quite going. So enter this guy named Leverrier. Leverrier was an extraordinary mathematician and calculator. I had the privilege of holding this folio of Leverrier's calculations, right? It was 200 plus pages of dense calculations where he took tables of people's observations of where Uranus was and deduced some, I think, errors in terms of this clock was slow. They didn't count for refraction here. And he predicted the existence and location of a new planet that would explain mathematically where Uranus was. Now, Leverrier had been a director of the Paris Observatory. But if you go to the Paris Observatory, there's a hall of the paintings of the various directors. And under the first painting, you see Leverrier. In French, it says, the translation is, alas, his ego was too big to fit into the halls of this institution. and that's true. Leverrier had a big opinion of himself. Now, he had good reason to have an opinion of himself, but it's just that he was not diplomatic about it. So they kicked him out. He went off, continued to work on the problem of this orbit of Uranus, believing that there must be some natural explanation. And that's when he deduced the direction of a mass. He came back several years later to the Paris Observatory and walked in and said, I have mathematically discovered a planet. It's in this general quadrant of the sky, but if you let me name it, I'll tell you where it is. And the audacity of someone to come in and do that, to say, well, I just, in my mind, have found this planet, and I'll tell you where it is if you let me give it a name.
I'm not gonna lie, I'm gonna give that one to him because
So,
that's pretty, like, he discovered it, right? Like, I mean,
well, yeah, but what happened was that the then director of the observatory, with the concurrence of his colleagues, threw him out. In fact, he forbid the great Paris refractor from going into even looking at that quadrant.
wow.
He refused to get this guy even, and so he had to write to his friend Jonathan Gall in Germany to say, look here and tell me what you see, because his friend had a great telescope. And in fact, the very first night that was clear after his friend received this letter, he points a telescope at it. Within a half degree, he sees an object, obviously a planet, this little bluish disk, and there it is. So Germany, now at the same time, John Adams was doing similar kind of calculations, but Adams was not as meticulous as Leverrier, and so his error was around almost 11 degrees. So it took a lot longer sweep to find Neptune.
Is that the different Adams of our President Adams?
Yes, it's the English. And so Adams declared it to be King George's star. And of course, people said, naming a planet as a star, that's kind of a dumb thing to do. And of course, the problem was that the internet back then was really slow. And even though Adams discovered it some, I think, months later, he didn't realize that Leverrier had done this stunt, and his friend in Germany found it. And so Germany says, it's our planet, we discovered it, we saw it. And France says, no, Leverrier, he's French, it's a French planet. And of course, English say, but we saw it. No, you saw it later, and you weren't as accurate, so you're English. And it was this whole big diplomatic thing between Germany, France, and England, all snipe each other. But eventually, it was kind of decided from actual dates that Adams was too late. He discovered it later than the guy in Germany.
I will say, based on this Wikipedia article, Adams was, according to how it's presented here, Adams was fairly open and about this. He seems to have given full credit. Once realized.
We realized at the time of the internet, when Adams discovered it, he thought it was first, and he had a period of time where it wasn't until they did learn that someone else on the continent had discovered it earlier and missed it, right? So he was accepted and bowed out of it. Became now this Germany and France argument.
Wow. Germany and France, they don't argue about anything ever.
Well, so Leverrier was actually accepted back. He became a director of the Paris Observatory again, and that the thing about that folio, again, we're talking about a large folio side. When he first, with white gloves, showed me the folio, I thought it was a typeset rendition until I looked at the thing carefully and said, no, his handwriting at first glance looks like it's typeset.
Wow.
His penmanship was just angel written to a fairly well. And again, dense calculations. We're not talking about a computer. We're talking about just hand grinding through calculations. And it wasn't until like page 190 something or other they said mass here, this distance, blah blah blah, that direction. That explains why would explain the deviation of Uranus off of what was assumed to be a Newtonian path. And he applied there, and so anyway, it kind of decided, okay, here's what we're going to do. We'll give the German the credit for discovering it, but we'll let Leverrier name it. So Leverrier actually was at a ceremony at the Pantheon, and all French noble, the French aristocracy. Well, the politicians, they had executed the royalty, were there, and they were anticipating, is he going to name it after this monarch, or this city, or how is he going to name it? And Leverrier still holds a grudge about being kicked out the previous time on the observatory, and then not just pointing at the telescope before he could discover it. He walks up to the podium after receiving the medal and announces to the crowd, as the text goes, he announced to the crowd, broke into a perfect, unaccented English, and said the name of the planet shall be called Neptune, which turned out to be the Astronomer Royal idea that Adams actually approved of, eventually convinced of for that. And the French were like, he just gave the English name when it's a French thing. And so it wasn't more than a couple weeks later they kicked him out as director. Again, because
wait, this was Uranus or this was Neptune. Sorry, Neptune, I got confused this whole time.
No, I'm sorry. The name of the planet shall be called Neptune. I'm sorry. I said I misspoke.
You said Neptune. I was thinking Uranus.
Yes.
But we're talking about Neptune. We're not talking about Uranus.
Yes. Yeah, we're talking about Neptune. So Neptune gave it that name. He announced that name in part as a snub for the French political aristocracy that snubbed him. He still had held a grudge. So they kicked him out again. He ended up having a whole thing about planet Vulcan and so forth. But again, it is one of the great tour de forces of just raw calculation, data reduction without mathematics. Amazing guy. So people are pretty happy that Newtonian mechanics found Neptune. By the way, Leverrier never looked at Neptune in a telescope. He said, I know where it is. Why do I want to waste my time looking at it? That was his. I predict where it is. I told you where it is. It's where it is. You found it. Why do we need to look at it? I know what it is.
That's so weird.
He was he was an interesting character. Yeah. But when Mercury started showing even greater signs of oopsies, right? Not quite Newtonian. Leverrier said, "I got this."
And he was the first person to notice it.
Yes, he said. By the way, blah blah blah,
Yeah.
and Leverrier said, by the way, just so there's no disagreements, I'll tell you, I'll calculate where this planet is, and you're going to call it Vulcan because it's the god of fire. It's the closest to the forge of the sun. So I'll tell you where it is. You'll name it Vulcan, and he spent time trying to figure out a mass. He ended up, I guess, his last set of calculations, he had 5 masses orbiting inside Mercury, 2 which were inside the sphere of the sun, trying to curve fit this thing, and just couldn't.
Yeah, that's what it looks like when you're trying to. If he had come down with one prediction, because for Neptune he had one prediction,
yes.
But I wouldn't be surprised if by the end of it, even he was like, "This is not quite working." But
yeah,
maybe not.
He didn't really live long enough. I kind of imagine, it's a thing where it wasn't until Eddington did the solar eclipse experiment after Einstein's general theory of relativity that helped explain the apparent irregularities of the motion of Mercury. So here's where we end up. And so he basically disproved the existence of Vulcan as a planet. Now, there may be asteroids down there in that zone. There's another zone that's between 0.08 and 0.18 AU. So 8% the distance, Earth-Sun distance to 18%. That's the next zone where an object greater than about 10 meters in diameter can orbit for 4.5 billion years. And people have been like myself, have gone to eclipses and tried to image in that zone. It's about 2 degrees away from the sun. So you can only really see it either through during a total solar eclipse, which is why I go to eclipses and take pictures there, or there's a new European satellite pair that's going to give us very long, many hours of eclipses, because basically one object is going to fly in front of the other and give us a long, super long eclipses. We haven't seen it. We've proven that assuming that an object on that zone has to be running at around 1,000 Celsius, given the temperature that is there. And so it needs to be screaming in the infrared from not being red hot, but pretty toasty. So it's not going to be a volatile thing. It's going to be a black Mercury-like object. And we know that from things like SOHO, there's nothing, and then other observations done, there's nothing that's bigger than 6 kilometers in diameter. We know on the other side of the coin that around 10 meters, if it's smaller than 10 meters, the solar radiation and various effects would have pushed it out of that zone. So I've done things where I've looked during solar eclipses down as deep as magnitude 14 to look for asteroids orbiting inside that zone. Haven't found any yet. There may not be any, but part of our goal was to not find something if it didn't exist. So we didn't want to have, because I laugh because there was, for a period of time after Leverrier and Vulcan, that all kinds of people claimed to be discoverer of Vulcan, right? All kinds of stuff. And it was flocks of birds to sunspot groups to just dust on people's lenses. I mean, all kinds of crazy things as to why it became kind of a crank thing for people to come in and say, I found Vulcan. and not have it pan out. But anyway, so we've moved into a model where relativity enhances. It doesn't invalidate Newtonian mechanics. It enhances and explains, especially in extreme environments around massive objects like stars and neutron stars and white dwarfs and black holes. But from our point of view of the 20th century sort of added on top of Newtonian mechanics relativity for those high precision things or those high orbit. And by the way, Parker Space Probe. So we have this probe that has an elliptic orbit. Again, as Kepler's laws say, that dies in close to the sun. It gets quite close to the sun. I think it's in number of solar radii away. And the last time I'm looking at, that the Kepler or the the Parker Space Probe is the fastest object, macroscopic object made by people. And the last pass that it had, the closest approach, its speed relative to the sun was 690,000 kilometers per hour. That's 430,000 miles per hour. And actually, it reached 0.064% the speed of light.
It's crazy.
So it zooms. Now, one thing I did was to put on board this spacecraft an atomic clock. And according to relativity, that atomic clock ticks 1 second per second. So that Parker Space Probe, for its environment, its frame of reference, 1 second is a second, right? And when it comes back out, when it survives the pass and comes back out, and we do this time sync, we find that Parker Space Probe has a different time than the Earth. Because the Parker Space Probe dies into a more intense gravitational field and its speed, etc., the relative effects show up, and we have to do correction. And so every time it comes back out, we have to fix its clock relative to now. Its clock is accurate. It's just that it's different. It's a different frame of reference than the Earth. Sadly, or happily, depending on your point of view, the error is exactly spot on where relativity predicts it should be. We were hoping to see a deviation because, again, this is not. We're not talking about some muon thing. So if we're talking about an object about the size of a bus that gets up to zooming speeds that goes deep into the gravitational field and has this relativistic effect that we can actually measure, and it's one of those things where, guess what, Einstein was right yet again. Now we may find a deviation later, but people keep looking. So we have a relativistic add-on to Newtonian mechanics. We have additional planets like dwarf planet Pluto to the model. What's the current model? The current model, we have major planets. We have dwarf planets. We have an asteroid belt that goes between Mars and Jupiter. We have a Kuiper belt beyond Neptune, by a scattered disk, and we have the Oort cloud even farther away. And we have a number of dwarf planets like Ceres, Pluto, Eris. Make just over a number of candidates that are there. That are what is it again? If you that are orbiting and stuff. So we have these zones, and this is the current modern model. The barycenter, the sort of the balance point of the solar system, is mostly inside the sun, but when Jupiter and Saturn are on the same sort of direction, the balance point is pulled just outside the photosphere of the sun. But that's our current model now. It's evolved. Again, we went from just vague guesses to what we like the universe to be like, to measurements, to mathematical models that might fit the measurements, to law of gravitation, to explain the models, to refinement of those models with more observation, finding those models were not quite correct, and Einstein coming in and essentially enhancing Newtonian mechanics with the general relativistic model that we have today. Now, there are certainly questions that still remain, but the general model of the solar system is now pretty well established as a fact. Whether or not there are asteroids in a Vulcan zone, we don't know. There's more things to figure out, right? With Vera Rubin telescope, we're going to nail down hundreds of moons of Jupiter and Saturn and Uranus and Neptune. We're going to sort of find more Vera Rubin in its 10-year span. We'll find more asteroids by an order of magnitude than the higher history of the human civilization.
Right.
Now, we will, at the first time, have a catalog where there's more objects cataloged position than there are people. Right? We're going to explode. So we're going to go to this model where you have things like Gaia that have their position, and Vera Rubin have a movie with 10 years to have a very accurate model of the solar system and the galaxy and so forth there. So we're moving forward.
Yeah, I know this episode was mainly about our solar system, but when did we discover that our solar system itself wasn't standing still? Our solar system was in orbit or moving itself.
The sun's motion wasn't the sun's apparent motion in the galaxy predicted when people were building models of what the Milky Way was like? No one expected the sun to be the center of the Milky Way.
Nobody.
Yeah, we could see that there's a dense bit of stuff towards the direction of the constellation of Sagittarius, right? Kind of a dense spot with arms around it, and we knew there was motion. I think didn't they use optical Doppler shift?
I don't know.
To get the apparent motion and early on. I know that Vera Rubin, as an astronomer, was somebody who was involved in measuring rotation of galaxies, including ours.
Yeah.
And she was the one who provided solid evidence that galaxies like ours and others were spinning too fast to go apart. Zwicky had predicted that there's more stuff out there than meets the eye, and people kept dismissing him. And he was kind of Leverrier-like character. He had a little bit of a caustic thing, but he was very good at what he did for a very good reason. And Zwicky was credited with proposing an idea. Vera Rubin, she was the one that provided the solid data of years of painstaking measurements to say there's more gravitational field out there than you can count for. Galaxies are orbiting clusters too fast. Galaxies are spinning too fast. Our galaxy is spinning too fast to account for stuff. And there's this 6 times the amount of gravitational field that we can account for. So people say, well, what caused the gravitational field? They say, well, mass. So where's this mass? I mean, astronomers are really, really good at faint signals. The problem with this mass, if it is a mass out there causing this gravitational field, is we've never seen it absorb a photon, reflect a photon, or emit a photon of any frequency ever. It appears to be complete. If it exists, it appears to be completely stealth to all frequencies. And astronomers are really good at faint stuff and faint reflections and faint absorption and so forth. Nothing is there yet. There's on average about 6 times more gravitational field than stuff. And Vera Rubin, whose name rightly is on the Vera Rubin Observatory, was the astronomer who provided the whole data to say, there's something and for it to call it dark matter, we don't know it's matter. It may be that, maybe that Newton's law of gravitation has some extra terms, or relativity has some extra terms at some scale we don't know about. Or maybe there's stuff out there that we haven't detected, but it's kind of embarrassing because it's like a lot of it out there. We don't know. That's one of the great mysteries right now. Dark matter and dark energy are like Mercury pre-relativity, not following Newtonian mechanics, right? It's something to pay attention to, and people are trying to figure it out. But unlike perhaps in the late 1800s, we're not just rationalizing it away as a.
I think that the most popular position by astrophysicists is that it is stuff of some kind. In that, and when I say that, I mean as opposed to a modification of general relativity, it is a thing that has mass and like exists at. You can map it. You can say where it is and where it
Yes.
isn't.
Yes.
And the reason that that's the general consensus is because we can say, or at least we think we can say, where it is and where it isn't.
Because we measure excess gravitational field by looking at bending of light coming through it.
Yes. Yes, exactly. In a way that is hard to make sense of with a sort of non-material model, but not necessarily impossible.
Yes, and there are things that various MOND. What do you mean by MOND? Well, that G and 1 number 2 are R squared. You say, well, we add a couple of terms if there's something else going on there, modifying that model. And the problem is that there are things that MOND does well and other things it fails at. On the other hand, you have to say, well, what is it? What causes what warped space? And we think, well, mass, energy, right? So there must be something there that's causing space to warp. And other people say, well, then where is it? What is it? Why is it stealth to electromagnetic radiation? Why does it appear to hover around halo of a galaxy, but not in the galaxy, and other weird things like that? And why do some dwarf galaxies have 100 times more dark matter field than others, right? It's not consistent. So that says stuff if it's like this guy has got a lot of it and this got a little bit. I don't like the term dark matter because it doesn't. What we observe is excess gravitational field or unexplained gravitational field. So I would call it dark gravity myself, but terms are there. So I don't know. So we've gone from early cave markings and calendars to sort of a geocentric models and people saying the universe is nice, so it must have these nice properties, and guesses to trying to fit observation and going to these wacky 55 sphere things and so forth, to people trying to say, well, maybe it's simpler if we put the sun in the center and blah, 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 and Mercury and Venus around, everything goes around the sun, except that circles didn't fit it. So eventually with Tycho being anal retentive in observations and Kepler extending it, and then getting insight that ellipses are nice things. And then there's properties of ellipses, that the Kepler's laws, that then Newton came around and says inverse square, da, 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 gravitational law of gravitation, da, 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 calculus, da, 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 except not quite. Leverrier, Neptune, Mercury. So we have to adjust a little bit, tweak a little bit to get relativity. And now we have our solar system. And by the way, just to be clear, Pluto is a planet. Astronomers recognize Pluto as a planet. Why? It's a dwarf planet. A dwarf planet is a type of planet, just like Ceres, Eris, Molia, Make, fourth core, Sedna. Those are all dwarf planets. And so we have the sun, the major planets. We have this belt of asteroid belts between Mars and Jupiter. We have these Trojans, these blobs of stuff. Again, we look at that diagram that's there. We have these these Jupiter Greeks and Jupiter Trojans and other things, piles of rocks flying around. Outside of that, we have the Kuiper Belt beyond Neptune and a scattered disk to the Oort cloud, and that's kind of the edge of the solar system, at least the influence of the gravitational mass that's the solar system. And that's our model today.
Okay, I have two questions. No one else has any. Okay, Chad has a question. Here's your time.
Sure.
I have two questions. First of all, before we get chat questions, Vandy, does any of your current studies affect our model of the solar system nowadays or in the past?
No, not really.
All right.
Not unless we were able to. So one of the things that work like mine ultimately may be useful for is measuring and constraining various dark matter models. And because the expectation is that, there should be dark matter kind of all around us. And there are effects that certain models predict. But none of those models are really likely to give any sort of new dynamics of the solar system.
But
really.
to misquote Fermi, where is it?
I'm
not trying to be mean. That's a big question.
It is,
and excited that they don't know.
Yes, but we would be a lot more excited if we could find it too.
Yeah. By the way, I'm resorted to drinking moonshine,
nice.
distilled spirit. It sort of is. It's a apple pie sort of thing here. But yes, please continue. You're talking about the dark.
Basically, the idea is that you can use that certain ideas of what dark matter might be, like ultralight or wave-like axions, might cause a very weak coupling to the existing interactions that we know, and could perturb the frequencies of atoms by a very small amount that you can measure with interferometry. And,
question: how much has people ruled out supersymmetric particles? Has that been?
Oh, it's pretty. All of the nice models of supersymmetry that made them attractive are ruled out. It's sort of at the point where we would have expected to find them by now, and you can keep on like making and adding stuff, but you have to push the masses heavier and heavier. If the natural form of sort of supersymmetry was true, then the LHC should have found particles a while ago. Possibly the Tevatron should have found particles.
Yes.
But it's still one of the better. We don't have a whole lot of good. We don't have any like great theories for beyond standard model physics. We just know that we need something.
Yeah, and this is again, this is one of the things about science, is that we are really excited that we don't know, because when you admit you don't know, you have the possibility to learn something. So not only do we say we don't know, but we're trying to figure out what it is and why. Now the in terms of energy, right? So you get a mass or energy, the same sort of thing. I think is the numbers now where 4% of the universe is particles, like protons and electrons, but quarks and neutrinos and pions, all this sort of stuff. And then 24% energy is in dark matter. Is that right? Around 24%?
Yeah, it's something around that. Yeah.
And then there's 72% is something else called dark energy, which has nothing to do with dark matter, we don't think.
Correct.
That's causing, as it the space behaves like it's repelling itself.
Yeah.
And the lambda
Space seems to
CDM,
make more of itself.
yeah, and yet dark energy seems to be not constant over time. And it
That
may
is,
not be constant over direction. Some of the surveys are suggesting that dark energy may not be this property, but there may be.
yeah. There, I don't know enough about the sort of cutting edge stuff.
Yeah, I mentioned it because the interpretation of the observations are there; they're being checked, but they're hinting at dark energy may not be this universal thing.
Yeah.
It may be something evolving over time or over space. There may be more stuff there than there. We don't know. And so the result is about 95% of the energy of the universe, we don't really have a good notion. So the standard particle model, great model, explains a tremendous amount, very successful, misses about 95% of the universe, which is a bit of a miss. It needs.
But the thing that people don't appreciate about the standard model is that for all of the answers that it does give,
Yes, it is
right.
extraordinary.
It is right about everything it's sort of trying to be right about.
Yeah, and don't give me this 120 order of magnitude worse prediction stuff. That's a bunch of BS. But the standard model is extraordinarily effective in describing an extraordinary wide range of phenomena in the universe.
Yes.
So it's not that it's wrong. It's just that there's a bunch of the universe that we don't know how to fit into a standard model.
Correct.
My second question, real fast, is I'm probably pronouncing this wrong. I always pronounce things wrong, but how does our knowledge
pronounce all those Greek things wrong? People are yelling at me for.
How does our knowledge of, I think it's called the Milovich cycle, affect our knowledge of the orbits? Milankovitch. Yeah, that's the word.
I don't.
Isn't that going to be more due to dynamics of the sun and not necessarily
I think
orbits?
that's more about precession of it. That's sort of about how the Earth rotating and the Earth wobbles. There is some effect of it getting tugged on by other planets, but it's also
in the sun, yeah.
Yes, in the sun, but it's also you still get a lot of a fairly rich array of effects, even if you only had the Earth and the sun. You do need the sun because you need, I think, something to like sort of break the symmetry. Although not for everything.
But you also need the moon because otherwise the Earth, like Mars, just tumbles and wobbles, right?
Yeah, things wobble, and spinning things wobble in all sorts of way, like genuinely. There are a lot of different ways that things can wobble, and they are not all the same thing.
We're not talking about polar reversal. We're talking about the planet's rolling on its side and up and down and so forth.
There is a great here, let me find it.
But while you're looking at that, explaining that the moon is Earth's moon being so honkingly big compared with just like a small rock, helps keep the Earth's axis relatively stable in its inclination to its orbit. So the Earth doesn't roll over the side. What's so big about rolling over the side? Well, the inclination right now is 23.5 degrees from the orbit around the sun. If the Earth rolled onto its side, let's say, so the inclination is now 90 degrees, you would have a situation where for half a year, the northern hemisphere, let's say pointing toward the sun, would become hotter than the hottest Sahara, hottest Death Valley possible. And the other side of the Earth would be colder than the deepest, darkest Antarctica. And you have violent winds from the expansion on one side blowing around the other side. It would just be, life would be pretty cranky if it could survive on a planet like that. The fact that Earth's orbit has stayed up relatively vertical is in part due to our moon.
So this is an effect. What's this is going to show is this is on the International Space Station, and there's this handle here that he's going to like basically unwind, and then it's just going to rotate freely in space. And this object has three different. It's not symmetric, and it behaves very weirdly.
It's like the tippy top.
It's like so this is a Veritasium video, by the way.
Yes.
It's from, I guess, 6 years ago, and it's also called the tennis racket paradox, because if you try and throw a tennis racket around the axis that he tried to do it is almost impossible to get it to rotate like that. You can rotate it along its long axis, and you can rotate it around its shortest axes. But asymmetric objects, when you try and rotate them around their intermediate axis, if you have any imbalance at all, you get these very, very clear, it switches, and then it seems stable for a bit, and then it switches again.
Yes.
And it's very weird. And this is just a solitary spinning body. It's a, quote, simple system. The mathematics of this are not simple, really.
No.
Yeah.
Yeah, Feynman was big on taking and gluing bolts to plates and flinging them around and noticing how they crash to the ground differently. He really enjoyed that. The mathematics of that was pretty. In fact, there's Feynman. Yeah.
See, there's Feynman for you.
Yeah, because I went into the office and there's a whole bunch of smashed plates on the floor, and I'm thinking, did you have a temper tantrum? No, I've been experimenting with this problem of blah blah, and I ran out of plates, and the cafeteria won't give me any more.
Yeah, we just have one question from chat.
Isn't the Earth's moon the fourth largest moon? I don't know.
No. It's. I mean,
it's the largest proportional to the planet. It's the largest of the non-dwarf planets, because
but like Titan,
and
Titan is the biggest one. There's also Ganymede and Callisto are pretty big. No, Moon is there, but I think in terms of let's not guess. Let me get the sizes of moons. So the list of 30th biggest moons, the 30th biggest solar system moons, because solar system, there's now so it is Ganymede, Titan, Callisto, Io, and the Moon. So Moon is number 5.
Pretty good.
So yeah, but I mean, Ganymede is 5,000 kilometers, 5,200 kilometers. Titan's 5,100 kilometers. Callisto is 4,800 kilometers. Io is 3,600 kilometers, and the Moon is 3,400 kilometers. So the Moon is down number 5, and it's down there for a while. I mean,
and the biggest moon is still smaller than our smallest non-dwarf planet.
Well, I mean, Ganymede and Titan are bigger than Mercury.
Oh.
So the geophysical definition of a planet has things like Ganymede, Titan, and our Moon as dwarf planets, right? They fit the definition of a planet, because it doesn't really care as to what is orbiting. Even if it doesn't orbit, if it's ejected from a solar system, it still is a planet of some form in a geophysical sense. But yes. There are and the number of moons of the big planets is just now being uncertain, because I mean Jupiter, I believe the current number of moons, I recall, it has 97 known moons. Jupiter. I remember it used to be 12. And Saturn has 247 known satellites.
Oh. Are any of the moons bigger than Earth?
No. No, none
So-
of them are, and most of them of Jupiter's 90 some odd moons, the if the Ganymede, Callisto, Io, Europa, the so-called Galileans, they are the heavyweights. The fifth moon is like a 4,000th, 5,000th the mass of there. So everyone else in Jupiter is puny rocks compared with, the two largest Galilean moons are comparable in Mercury in size. So, when Vera Rubin does the final, does the begin to do the full sweep, we're going to find, hundreds of moons orbiting Jupiter and Saturn. There's a lot out there, but yes. Yeah,
well,
you
I'd
heard
love
right.
to talk.
274 known satellites.
Well, I'd love to talk for more, but it's getting to 2 a.m. at my time. So, anything you guys want to plug or advertise?
I do Bad Science Sunday on Maya's channel every Sunday. I can't remember if I'm also doing Bad Scripture Saturday on Kip's channel this week. I can't remember which week it is, but yeah.
So one of the things I do on Debate Prep is the Volcano Show. And on October 17th, on Chesh's Debate Pub, we're going to do a Volcano Show at 20. That's 8 p.m. Pacific time, where we'll look at what Kilauea is doing, as well as volcanoes in general. Last time we had Maddie from Science Head Up join us to talk about atmospheric phenomenon with volcanoes. Check out this one on the October 17th. So it says you live not far from Feynman as a kid. Yeah, he's buried 3 blocks from where he grew up. Yeah, give or take. Yeah, and I had the pleasure of being taught special and general relativity from Feynman.
As for me, I have nothing planned at this time, but schedules happen and go. And if I do, Jillian Chat might be a guest on that. She's usually a guest on my channel this year.
Yeah. Again, I apologize for the pronunciation of some of those historical characters there. Those kind of pronunciations are not my forte or fort, depending on your interpretation of that word. We don't know everything, and we celebrate when we don't. We get excited when we don't know. And as Dr. Eagle says, there's a whole bunch of stuff relating to whatever is the dark gravitational field and this dark energy thing that we're exploring, because it's there. We know it's there, but we haven't figured out what it is. And that's an exciting thing to try and figure out. I don't know who's going to find it first, whether it be a particle detector or an observation out in space or someone with extended model. It's hard to say what it is, but we're learning a lot. The universe continues to impress and do things. There's a whole bunch of frontier things with regards to quantum mechanics and general relativity that are up for debate. So we're trying to figure that out too. There's some amazing space probes going around there. There's some really, space is now quite active with a bunch of interesting objects out there and experiments. One of the things we certainly hope to do eventually is to get some return samples from Mars, but that's got to be planned. I think probably most recently, probably the big thing in astronomy is the Vera Rubin telescope, where the data coming off of that thing is going to give us an enormous view on our solar system, our galaxy, and objects. I'm really pleased. And again, it couldn't have been named for a greater astronomer than someone like Vera Rubin, who was an amazing person who contributed a lot to our understanding of our universe.
Well, if you have any future questions, say so in the comment sections below. I'll forward it to the experts. But in the meantime, never stop learning and enjoy the randomness.
Yay!
We'll see you next time. Hey, thanks for watching my podcast or Let's Play. If you want to help support my channel, you can make a monthly or yearly pledge on Patreon, or just a one-time donation on Vimeo, PayPal, or Cash App. For those looking for something to wear, we have some shirts, hats, and other stylish things in our merch store. If you enjoy gaming, you can always follow and sub to me on Twitch. For those who don't want to give money, I have an Amazon and Steam wish list who can help the channel out. And of course, just liking, leaving a comment, and sharing this video helps more than you can imagine. And always remember to never stop learning and enjoy the randomness.